Even go outside. It's a beautiful day here in Southwest Colorado. My name is Mo Rock, and I am the programs coordinator at Southwest Water Conservation District. And I'm going to introduce our next keynote speaker for this afternoon. Dr. Raj Khosla is the head of Agronomy at Kansas State University and globally recognized authority on precision agriculture. And we are excited to have him all the way from Kansas today. And I hope he can give you a better introduction on who he is and what he does, and maybe how AI can help us with water resource issues.
Thank you, Mo. Yes. Good morning. We can do better. Good morning. All right, now we're talking. For those who have heard me before, know that I always do a live test to make sure that I'm talking to a live audience. So you guys passed the test. Mo, thank you for your kind introduction. It's good to be back here. I am not too far from here. I spent almost 22 years at Colorado State. And in 2020, I moved to Kansas State University to assume an administrative role that I am in right now. And as I was moving away, we got a $10 million grant for the the Colorado River Basin project. So although I moved to Kansas, our work keeps bringing us over here in the basin. It's a 6-state project. So it involves California, New Mexico, Arizona, Colorado, and then we have some partners, one in Georgia and one of course, in Kansas as well. All right, so just to give you an idea, let me see if this clicker will work. Okay. Point that way, okay. Okay, try now. I'm pressing both buttons. Okay, here you go. All right. Thank you. So that's where I'm currently located, and the other star that you see is when I was in Fort Collins for 20-some years before moving to. It doesn't look like this clicker is working. Okay, I have quite a few clicks. So Elaine, you might get tired, but it usually syncs really well with what I'm doing. So. Kansas State University is also a land-grant institution, just like Colorado State University. Okay, next. Yep. All right, and it has a beautiful campus. Many of you may have been to Kansas State University. That's one of our admin block. It's a limestone campus, really beautiful, but of course, it's in the humid half of Kansas, so it's pretty lush green. My clicker is coming back to me. What I want to share with you is the precipitation distribution in Kansas. It goes from, click again, goes from forward please, goes from low 400 millimeters, so that's just 10, 11, 12 inches, and all the way very high for the time you go to south. I got a clicker. The bottom one, okay. All right, so by the time you get to the south east Kansas, it goes up very high to 1,200 millimeters, so we're talking more than 45 inches of precipitation. But as you come closer to Colorado, you all are very familiar with that, and that's not different. Wheat is one of our major commodities. But I want to share with you that where wheat is grown. Wheat is grown in the western half of Kansas, and that's where it's water deficient. But we happen to be sitting on Ogallala Aquifer, one of the world's largest freshwater aquifer, and you can see by looking at these pixels, these are the GIS pixels where wheat is grown. And this is the current status of Ogallala. So water is very precious for Kansas as well. I know water is very precious in Colorado. I have learned that very carefully. So all the dark brown and orange that you're talking about, That's where Ogallala has receded more than 60%. And when you think about the frequency of droughts that we're experiencing right now, it's not going upward. So something got to change. What would that look like? Okay. So precision agronomy or best practices are very important to Kansas. In fact, agriculture is our largest industry. 42% of GDP relies on agriculture. These are some of the commodities that we grow. So I just want to set the stage up that water is important, not only in Colorado, but many other parts. And it's a precious resource. I'm now going to switch gears and ask you to imagine. I want you to imagine how agriculture may look like in 25 years from now, by 2050. What would be your answer? Drier. Moving north. Smaller. Resilient. Now we have some optimists in the crowd. Resilient. That's what we're talking about. Well, none of us have a crystal ball. It's very hard for us to predict what's going to happen in future. But Elaine and the organizing committee reached out to me to talk about, hey, how are we going to embrace artificial intelligence in agriculture? So instead of looking into the future, how about we look into the past? So here's a picture for you. What do you think this picture is? You have to speak louder. I heard somebody say computer. Yeah. And it has wheels on it, so it must be a mobile computer. Okay. Well, it turns out that this is the first global positioning system receiver that was put together in 1976 by Rockwell Collins. Now, how many of you use GPS? Come on, everybody's carrying that in your pocket. Okay. And so even the scientists at NASA had no idea that in the less than 20 years, this one GPS receiver that will fit maybe one on the stage, you can hold it on the tip of your finger. And if you bought a cell phone after year 2000, it's there. It's everywhere, right? It's in your cars, it's in your cell phone, and lots of other things. So this is one of the first units that were put together for military warfare, GPS unit that's being used by our soldier. And this is one of the makeshift unit. This is me working in northeastern Colorado, late 90s, using with the Trimble unit, and I have a tackle box on the back with multiple deep cycle battery. And then I'm wired myself, I'm wearing a Velcro with the analog data logger in those days, and I'm using RS-232 port to connect that to the GPS, and I'm going across the field measuring nitrogen stress in crops. Well, we have come a long ways since then, haven't we? Somebody said resilient. Everybody knows Einstein, right? And he said, idea is more important than knowledge, and I couldn't agree more, because think about it. What started as an idea in late 1980s, put together by this person who's the father of precision agriculture, late Dr. Pierre Robert. In a meeting like this, during that time, there was a lot of talk about that GPS is going to be available for civilians. And so the thought process was that one day when GPS become available for agriculture, we're going to connect everything that we do in agriculture with GPS. And then this schematic from a napkin was put together by a designer, and this has happened. What we're doing in agriculture today has connection to GPS. Location is important. But the founders of GPS cautioned us. They said when you start doing location-based agriculture, you'll be collecting a lots and lots and lots of data. And they're right. Today, for those of us who are engaged in agriculture, whether you know it or not, you're collecting lots of data. So whether it's past year yield, or what's in the soil, or different soil profile, there's tremendous amount of data, and I'm going to show you some examples. So as you look into the future, what's going to happen is that data and data analytics will be integral for the success of agriculture. Some of you may have read the USDA Agriculture Innovation Agenda that came out in 2020. And it talks about that in the next 30 years, i.e. by 2050, we're going to increase our ag production by 40%. Now, how many of you think we can get there? Show me a raise of hands. Okay. There are some pessimists in the crowd. Actually, U.S. is one of the countries that has been increasing our food grain production by 1.43% per year for the last 60 years. So getting there, we'll get there. No doubt about that. There's always a caveat, right? And here's the caveat. The caveat is that we're going to get there with 50% less footprint, and we're talking 50% less water and 50% less nitrogen. That's the catch. 50% less water, and yet producing 40% more food. How will we get there? So again, let's take a look at the history. So in 1900s, and I picked up corn as an example. I work a lot with corn. So our average yield in 1900s was 28 bushel to an acre. So let's call this an acre. Okay, and I have it in hectares as well. So that's about the land mass it took in 1900 to grow 28 bushels of corn. What happened by next 50 years? It dropped down to 3/4. Okay, so we increased our yield by 135% in the first 50 years since 1900. What happened by the turn of the century? With hybridization, mechanization, integrated pest management, new cultivars coming down, more resilience, right? All the approach that we have taken has brought now what it took 1 acre by 2000, it took less than an acre to produce the same amount of grain. What has happened in the last 25 years? It has come down further. And so, to translate this into what USDA Agriculture Innovation Agenda calls for, that by 2050, with 50% less water, with 50% less nitrogen. This is a very tall ask, but we have to be ambitious. We have to aim higher. How would we get there? And this is where I put as a hypothesis, could artificial intelligence play a role in helping us bridge that gap? How do we get there? So let's take a look at what is intelligence before we talk about artificial intelligence. So intelligence is our capacity to retain tremendous amount of observations, use our logic that we come up with observations, emotional intelligence, learning and observations, more observations that we continue to integrate. And it starts right from our childhood. Our ability to fit through shapes and sort them, which comes with observations, we're sensing, ability to read, ability to write. This is all where the intelligence is being formed in our mind. Ability to walk, ability to bike, observations, learning, logic, abstract, ability to solve problems. Ability to solve complex problems. Right? It's total observations all the time, infusing logic into that. And we're not the only species that's gifted with intelligence. There are so many other animals that are So for example, how ants will navigate towards food in a very organized manner. Or elephants, or dogs, and pigeons, and orangutans, crow, pigs, dolphins. The list goes on. Last year, there was a paper published in one of the world's top journals of science. So this is coming from Indonesia. Indonesia and Malaysia have a lot of orangutans. In fact, they have too many. But these guys are very intelligent. So this is an observation. Look at what happened like mid-June, 2 days before this orangutan was injured. But he knew which tree to go to, take the leaf, crush it, and put the sap on his wound. And take a look what happens 2 months later. In fact, there's a video on it. You can go online and watch it. So we're not the only intelligent ones. But Alan Turing, the father of artificial intelligence, he started this whole paradigm. Can machines think? And what would that look like? So he started in 1950 a totally new domain of intelligence called artificial intelligence. And of course, computers are machine. And the idea there is that can they mimic human behavior? That's the key question. And our fascination for machines are not new. All of these are examples of machines. How many of you knew that the glass sitting in front of you is a machine? You go to a river, you're thirsty, what you going to do? You don't have a glass. Right? It allows us to do more, right? So here are some now 21st century machine examples that are being used in agriculture. Most of them are robotic farms, and they are mainly focused on weeding. Farmers have very little tolerance for weed. They suck up your water and nutrients and so many other things, right? Most of them are on weeds. So this is carbon robotics. I've observed them, a whole herd of these, at least in California, and high-value crops. So I have a short video here. Elaine, if you click anywhere inside that. Oops. Just anywhere inside that picture, that will do it. It's all right. So the machine has a what's called 3D vision. Don't worry about it, Elaine. Has a 3D vision. I'm sorry. And so it's looking at, they took a lot of data without any laser. And they specified the object of interest. So object of interest could be lettuce, a carrot, a radish, whatever that be. And then they also take three-dimensional images of everything else that the camera is observing. And then somebody have to sit through. Before artificial intelligence happened, there's a human intelligence part. Somebody has to sit through and look through all sets of those images to tell this is lettuce and this is something else. And something else needs to be zapped. That's what it is. Because you don't want to be zapping lettuce, right? And that's exactly this. So the video is showing you in motion exactly what it does. It has a very close to 100% accuracy rate. But then there's some other ones that are performing so many other different functions that are important for vegetable crops. Right now they're being used in horticultural crops, but soon it will be used for row crops. Okay, I want to show you, this is one I know is coming from Florida. This is a totally autonomous spray system that can do 24/7. It incorporates, it does fumigation of the orchards, so there's no human intervention, and you can place it, and they can work day or night. Where are these machines coming from? Well, this happened to be all 2 years back at the robotics show in California. If you haven't participated, if your time allows, go and take a look what they're working on. But our fascination for robotics is not new. This is 1957 movie. Hang on. Okay, just click anywhere and then don't do anything. Yeah. This is 1957 movie. So the farmer and his significant other, and constructing a vision that in future we'll have machines that will be totally autonomous, and they were visioning it will look something like this. And not just one or two machines, you will have a whole herd of those machines that can go through the field, right? And this is 1957. Of course, there will be towers. He's looking at the spatial map, distribution of heterogeneity in soils and crop, and then it will start flashing somewhere. So they say, hey, there's a problem there. And so he's going to throw his hands up in the air. You see, he's concerned right now. Right there. And then he will send a signal to the machine to fix it. So our fascination with the robotics is not new. This is my very good friend and colleague. He's no more. He passed away last year. Dr. Simon Blackmore, one of the iconic figures at the University of Harper Adams, who did a lot of work on robotics and automation. And in Denver, not too far from here, in 2008, he was the opening keynote speaker for the International Conference on Precision Agriculture. And he talked about that in future, there will be a whole swarm of robots that will be going through the field. And he was right. In 2017, 8 years back, at Harper Adams, they made a press release, some of you may have read this, the first hands-free hectare, 2.5 acres. They grew 2.5 acres of barley from land bed preparation all the way to the harvest with no human intervention. Now, this is the most expensive barley on the planet, I get it. But they proved in 2017, in fact, at Harper Adams, they are still running the hands-free hectare farm where there's no human intervention. I've been there, I've seen it myself. So when we talk about AI, how would AI be infused in agriculture? This is only a partial list. Robotics, I've already shown you some examples. Ability to monitor soils and crop. To detect insect pests and diseases, I'm going to show you some sensor and sensing technology that's coming down the pipeline. Disease diagnosis, and we're not talking about diagnosis disease when it has happened. Asymptomatic detection of diseases and pests. It's coming down the line. Predictive analytics, ability to not just guesstimate, but quantify what production may look like when you couple with the location, climate, weather data, the crop of variety you're growing, soil parameters. Intelligent spraying. This is a lot of companies that already have some units out in the field. And what kind of production we're going to see in future using AI. But at the core of all of that is one element, and that's data. So how many of you would believe or agree with me when I say we know how to farm the land? Raise your hand. Okay, quite a few. Going forward, what we need to learn is how to farm the data. How to farm the data. Because we cannot continue same old business. Such a live panel this morning talking about the challenges and some opportunities related to better management of water. If you look at the history, the entire civilizations have prospered in the vicinity of water. So water is very critical for our survival, not just sustaining, but thriving. So data is the hallmark, and we're going to employ machine to help learn the anomalies in those data, the patterns in those data. So we'll have to train machines repeatedly, over and over and over again. Because what are we doing with our central processing unit, the one I'm pointing? We're training our central processing unit since we were born. And so we'll have to do something similar. Now in agriculture, the data is very fragmented. It's very fragmented. We're not willing to share the data, right? And that's a total different discussion. And not only program the data, but then you have to test it. And what may work in right here in Ignacio may not work in Fruta or other parts, right? And there has to be algorithms. And if somebody comes to you and claims that they have the algorithm, please doubt them. Those algorithms do not exist right now. Our lab has been working for last many years to develop some of the algorithms. In fact, my PhD students who graduated last year, he now works at Colorado State University, and he's running the CSU TAPS program, the water testing and performance program. Okay, so agriculture is complex. Do we have a consensus here that agriculture is complex? Okay. Agriculture is complex because they have so many moving parts. And if you're working with a row crop, you're given 100 days or 120 days to make all these decisions with genetics, with water, with soil, with marketing, with spatial variability, with machine, with market pressures, what my neighbor is doing. What did I learn from last year? There's so many moving parts in agriculture. How much am I going to apply, where, when, whether it's water or nutrients? So what's happening is that all the complexity is put on the farmer, the producer, with such a significant expectation of being champion of sustainability, but you have very limited choices. You got some machines, just like this one. In this case, this has a GPS on it. But we're looking at agriculture through the lens of a machine, and that machine is computer. Now, computer only understands the language of zeros and ones. And that's captured in form of data. So the computer will only as good as the quality and the quantity of data that's being infused into the machines. So going forward, there will be huge amount of data collection that must happen, that must be trained, and the machine has to learn that. Robust algorithms needs to come through, and this is only a partial list. And so what do? You put all of that onto a cloud server. Just like when you take a picture from your phone, it goes to a cloud server. You can share it with your family, right? It has to go to a cloud server. And doesn't matter whether you're an Apple user or some other platform, doesn't matter. It has to talk cross-platform. And not only that as a producer, you could be standing anywhere in your field or in your office, doesn't matter, but you have to have access to the data. So one thing that has happened is the accessibility to GPS, Global Positioning System, as you see in this picture, right? And then for the last 10 plus years, we have drones, which are allowing us to quantify, one, collect data, quantify heterogeneity in space as well as time. So I know Dr. Perry Cabot is sitting right up front here. He's one of my main collaborators on the Fruta research station where we're working on AI project. We collect data throughout the growing season because we're trying to learn the change detection in crop canopy. And more recently, there's a whole suite of sensors, wireless sensors and devices that are coming down the pipeline. And so if you look at this like 5 or 10 years back, a soil moisture sensor node may look something like this. In fact, this is a picture coming from 2012. So you have a 12-foot tall post, a data logger, 5 cables that are connecting to the 5 soil moisture depth. You have telemetry, you have solar panel. Cost of this sensor node, one sensor node, $3,000 to $5,000. Do you know how many sensor nodes do you really need in a 100-acre field? Any guesses? Good guess would be a lot. We have done statistical analysis on this. You need anywhere from 80 to 100 of these sensor nodes if you really want to collect the data that allows you to apply the right input, in this case water, at the right time, at the right place, in the right amount, and in the right manner. You do the math. If the sensor node is going to cost you $3,000 to $5,000 and you need 100 of these, nobody will sign up for that. So something got to change, right? And with that hypothesis in mind, I'm going to show you some more information here. We are working on the next generation of sensors. That will be micro sensors, have no battery. These are called passive sensors, inexpensive. The idea is to mass produce it for pennies. Yeah, for pennies. That you can literally take it in your hand and basically just distribute it out on the field. And they are made out of biodegradable material. So they dissolve over time in soil. So you don't even have to go out and collect. So what happens, your field then becomes an internet of soil, or internet of soil moisture, or internet of soil nitrate. Again, you're collecting X, Y, Z information along with the parameters of interest that is fed into the model that allows you to apply the least amount of water when it's most needed so you get the biggest bang for your buck. I mean, think about it. If we have glasses sitting in front of us and all glasses are full, how many of you drink the entire glass? Likewise with plants, right? We want to spoon feed the plant, not quite one plant at a time, but maybe close to the plant. And so this is a prototype that in 200 days it basically dissolves in the soil. There are also in-planta sensors that people are working on. I'm going to show you some real examples. This is an in-planta sensor that you can actually just paste it on the leaf to give you parameters of interest. So what's going to happen is that, look at the bottom half of my slide. The plants, there are numbers and numbers and numbers coming from soil, coming from plant, and it would have no meaning unless we can translate data into information that allow us to make better decision making. And what is it that we're trying to do? We're looking at soil heterogeneity and the limited amount of water that we have, understand how weather and climate behaves at each location, collect a lot of data, use technology for crop management. So that goal has not changed. So let me just talk briefly about the sensors and sensor technology. I'm sure you have heard we can only manage what we can measure. And so if water is what we're trying to manage more efficiently, we need to make sure we can measure it, right? And we're at the cusp of revolution when it comes to sensing technology. And what's happening going forward, that these sensors are going to be rapid, reliable, diagnostic. So it's not a surrogate measure that we think what this is, but it's diagnostic. And it will be in place in planta. You can wear it. How many of you know about smart diapers? It's the same sensor. It's in the diaper. When the humidity of the diaper changes, you get a text message. Yeah, these smart, how many have heard about smart Band-Aids? Yep. It's coming. It's happening. So Internet of Soil, Internet of Plants, again, and these are degradable and inexpensive. They're inexpensive, that's the key. Batteryless and early or asymptomatic detection. So I'm going to show you a couple examples. And we're not talking about taking one measurement up here, taking us, hey, how much you guys would like to eat bread, omelet, and stuff, and then serving the same food to the entire. You understand? We're not doing that. We're going to be able to collect data from each and individual location so that we can site-specifically provide the information that they need. There's a report that I'm a co-author of, Science Breakthroughs 2030, published by National Academy of Sciences, 228-page report, you can download. So these are the basic scientific principles of what our sensing devices look like. But think about it. These are the scientific or technological names, and that's what these are. Early and symptomatic stress detection. So let me ask you, how many of you believe that plants cry for help? Anybody in the audience? Oh, quite a few people in the audience. Well, that's the hypothesis for one of our colleagues in Israel. They worked with tomato plants, and they imposed 3 different types of stresses, and they used acoustic sensor to quantify that. Number 1 was soil moisture stress. Number 2 was physical stress, and number 3 was radiation stress. In life, these stress don't happen one at a time, they happen all together. So what they did, they studied the data of causing stress to the plants, one at a time, and then they commingled the data together, fed it into the neural networks, what is called machine learning and artificial intelligence, and they were able to accurately detect the pattern or the source of stress every time, whether it was from moisture or physical or radiation stress. And there was a signal that I know we can't hear. The video and sound is not working very great, but that's all right. You get the idea. Here's another group. This is from North Carolina State University. They have these implanta sensor that measure the stress, that signal given out by the plant when diseases happen. Because there's a change in the volatile compounds just in the proximity of the leaf, which happens 3, 4, 5 days before the symptom appears on the plant leaf. How about that? So they can detect the virus or the pathogen that's going to infest the plant and cause the source of disease. How about that? You as a producer, imagine knowing 4 or 5 days ahead of time that a set of plants are going to be exposed to a fungal pathogen that might kill the entire crop. So it's coming. These are basically based on printed sensors. I didn't know there's a field called printed sensors. In fact, I didn't believe it, so I went to the lab and I saw it. You can use conductive ink to literally print sensors. Okay? And so we have been working on this field for the last 7 years. We screen through a whole bunch of degradable material. Then we do a lot of analysis in the greenhouse to make sure that it's going to last through our plants. Whole generations of what will happen to that. And of course, damage happens to the sensing devices. And we have published papers on that. This is an example of a soil moisture sensor. So you take a biodegradable material, and then you create a stencil, and then you print them with a conductive ink, usually silver or gold, but don't think you'll get rich with that, okay? It's a penny sensor, okay? It's a very, very, very thin layer of the conductive ink, and then you etch it with acid so it's become conductive, and you attach wires to that, and you encapsulate with that, and you add a circuitry board. That's your soil moisture sensor. It's pretty easy, and of course we do a lot of testing with wired sensor before we take it out to the field. And just want to quickly share with you, so starting this year with Dr. Cabot's help, we're going to create a test bed of these wireless sensor nodes, 24 of these, and at 4 locations, 2 locations in Kansas and 2 in Colorado. And this is the test bed we did in Kansas before we go out in the field. Here is a tower. So you send a radio signal, these sensors wake up for a millisecond, measure property of interest, and almost instantaneously will give you a surface map. This is the moisture distribution in your field. And so now what you're dealing with, you have an X and Y and Z depth and time T. So you're dealing with 4-dimensional data set, right? So it's like, when dog catches a car, what you gonna do with it, right? That's the paradigm we're in. So we're collecting so much data, and we don't know what not to collect right now. So you can collect this data every 30 seconds, every 30 minutes, every hour, just the way you want to program it. But there are so many questions related to that how do we integrate this data? What does it really mean? And we've also installed a precision lateral on the Fruta research station where you can control the level of water at every nozzle level. And we're trying to develop a prescription map. So let me show you. This is the Fruta location where we're doing this work. This is the particular field. It's about 12 acres in size. 12 acres in size. And so we go out and measure the heck out of it because we don't know what not to measure right now. And we start stacking those data layers. We do electrical conductivity. These are all soil parameters, but a soil moisture sensor system that we have been measuring the hard way, but now we're going to measure the easy way. Of course, the crop canopy through satellite imagery and UAVs, and lots of crop biophysical parameters, all are related to the yield. So when you collect this much amount of data, it's beyond the human capacity to really query that data and translate that into a prescription map. So this is how the soil moisture sensor network will be distributed in the field starting this year. And we have a lateral. So the idea is that we develop a prescription map that the sensors are talking with this lateral that's going across the field, and it's changing the prescription of how much water needs to be applied and where and when at every nozzle level. So that we apply the right input at the right time, at the right place, in the right amount. So this is my very last slide. So I want you to imagine what we're trying to do, and I couldn't figure out what's the best way to convey my message. So think about you talking with your smartphone, right? Which is enabled with the algorithm that our students and postdoc are trying to develop. So you say, hey, when should I irrigate this cornfield? That's you ask the AI part, right? And using the algorithm that's running in the background, it says, hi, Carl, let me ping the soil moisture sensor network, weather data, and it instantly creates what's there. That, hey, we had rain 2 days back, so now, in the next 2 days, the crop needs this much more water. So he says, you can consider irrigating tomorrow. Okay, so then Carl says, how much water to irrigate, right? That's a fair question. He said about 1 inch would be sufficient, right? And then he says, well, I need a prescription map to upload it. There you go. Almost instantaneously, it creates a prescription map that gives it to you, and then you say, hey, go ahead and upload it on the system. All right, he does that. Now listen, this is an AI. If the AI is working correctly, it'll say, hey, do you want to fertigate the field? And says, no, I don't want to fertigate the field. He said, do you remember what happened last year? That corner of the field, you lost 20 bushels over there. You still do not want to fertigate? Carl is scared now, right? Okay, then upload the prescription. And so it's uploaded and says, set me a reminder. Thank you. Okay, floor is open for questions, and I know Elaine was walking around, or someone is walking around with the microphone. Okay, there are 2 questions right here to start with. There's one up front and then...
Jude Chenemeyer, Montezuma Orchard Restoration Project. So my question, it seems like you've got a good view of what's happening here, a better view than most people do. My question is how close are we to having this technology, realizing in this technology, I mean the ability to pull out a cell phone and look at a plant, realizing you've got to come up with data sets for eggs of a pest, data set for larvae of a pest, data set for bacterial pathogens, viral pathogens, fungi pathogens, presumably the ability to scan what's happening with the leaves, what's happening with the vasculature of the plant, things that the human eye can pick up on,
right.
But presumably the technology. So how close, from what your perspective is, how close are we to being able to do this with a cell phone to where we can look at a plant, pull up an app, and
Right.
nail that?
Right. So cell phone primarily operates on the optical side versus the work that is going on worldwide. Optical is only the small spectrum of other. So for example, cell phone at the current time cannot detect volatile compounds. Okay. And so there's it's a whole diversity of spectrum, and that's why I showed you the sensors, the smell type, the sound type, the optical type, the feel type, mechanical, all of those being employed right now in order to really further this branch forward. And it's happening faster than you and I think. Now, it's not integrated. People are working in their different laboratories. It's not integrated. So we will need some agency who's willing to stitch it all together to accelerate, because farmers is not working with nitrogen alone or water alone. Pests happen, weed happen, disease happen. You know, what is the best planting geometry? What is the best planting date? Which variety? The questions, and that's why it's an understatement to say that agriculture is complex. Yes, we have a documented history of growing 1.43% per year for the last 60 years. So we know how to farm. But now we're looking at very different view angle, where we're infusing tremendous amount of measurements in order to be able to achieve what we're setting ourselves for. So, yep, and there's a question right behind you.
Hello, can you hear me?
Yes.
Hi, my name is Amarina. I'm with Dolores Watersheds Collaborative. I'm curious, you're talking about wanting to increase yield with less inputs and less land. From a permaculture standpoint, diversity of plants in one location indicates that we can increase yield of what we can eat and grow from a smaller acreage.
Yeah.
And it seems like the paradigm we're looking at in these slides is a kind of monocropping standpoint. And I'm curious if you considered permaculture in your research.
Yeah, we have not considered, but Amber, you're exactly right. Some of the way the policies and the incentives are tied up are kind of lopsided, where producing volume of grain is rewarded more versus how much carbon you capture in your soil, right? And of course, there's a developing carbon credit market right now, but you're exactly right. Is monoculture the answer? If you're asking me, I would say no. And so where does biodiversity fits into this, right? And that's not the part of the discussion that I was asked to engage in, but absolutely, I would encourage you and everybody in this room to be creative and innovative, bringing in different diverse species into your production system if you can, to enhance, more resilience to pest, more resilience to weeds and disease, and productivity as well. Yeah. Okay, last question, I was told. Okay, over there, back there.
Hello, Juan Perez with Water Education Colorado. I just keep having this question in my head. We also know that AI tools require a large amount of energy in order to maintain the computers, so is water. And so I'm curious if there has been any analysis looking at, are you including the efficiency of the farming usage of being more, water efficient versus how much water goes into maintaining the tool running or the infrastructure?
Yeah, so you're right, it's a very heavy consumer of energy, but how many of you know what is the largest energy footprint of agriculture? What component? So I hear example tractor. What was that? Transportation. What was that? There you go. Nitrogen is the largest consumer of energy, just one input. It consumes 2 to 3% of global energy consumption. So if you can cut nitrogen by 50%, my time is up. Thank you so much. I'm happy to be here.